Hi, good afternoon, everyone. I'll be very quick. I know everyone's waiting for cocktail hour, so yeah. I'm a machine learning tech lead. I work on Facebook's video recommendation systems, and I'll be presenting on trends in video recommendations. So I'd like to start by mentioning that this is a very high-level overview of the work done at Meta and across the industry and academia. I'd like to also extend my special thanks to the video recommendations core ranking team and to leadership at Facebook for their constant support throughout the years for this work. This talk will go over an introduction to video recommendation systems. We'll discuss trends and challenges. Many of the trends are also very new in this area. We'll then deep dive into challenges in multiple areas in the stack, along with solutions to some of them. And then we'll go over quick takeaways from this talk. So as you can see on the left side of the slide, 92.7% of global users watch digital videos every week. So this is pretty huge scale. So you can imagine that this is a very big use case. On the right, you'll see that in the US, people spend an average of 2 hours and 10 minutes daily across devices watching videos. And this trend is increasing year over year. Today, there are multiple products serving different use cases in this area. Like there is Facebook Watch, there is Instagram Reels, YouTube, Netflix, and TikTok recently. Most video recommendations have a common vision. That is to help users find, enjoy, and create interesting video content to strengthen their relationships, create communities, and realize economic opportunities. So basically, this vision can be broken down into three parts. Users finding, enjoying, and creating content is basically serving consumers and creators. Interesting video content is the relevance piece of it. And finally, it's on jobs to be done by the recommender systems. We'll then go into trends and challenges in this area. Before that, I would want to introduce a typical video recommender system. Basically, it's a multi-stage ranking system that is operating under computational constraints. So you can imagine that there is an inventory of billions of users at Facebook scale, billions of videos at Facebook scale also. So all these videos first go through the candidate generation phase, which is filtering from billions of videos to high thousands of videos. The goal here is to find somewhat related videos to the user. This stage needs to be scalable and is composed of like inexpensive models and rules. The next stage is the early ranking stage, which again gets it down from the high thousands to the low thousands. Here also there are ML models with medium complexity, needs to be again fast and scalable and have cheap inference cost. Finally, we have the full ranking stage. Here is where we have our highest complexity ML models to optimize what is left. And predictions from here are sent to predictions aggregation phase. In this stage, we aggregate all the predictions to get a final score per video and sort it then in the descending order of the score. In this stage, we also combine with a lot of business logic, like combining with integrity rules to downrank integrity violating content. So trends in this area. Video recommendation system generally is a multi-stakeholder marketplace where you have different stakeholders with diverse goals. For example, you have users who are trying to find the most relevant content. You have creators who are trying to get distribution for their content. And then there is a platform which is trying to combine these two and realize economic opportunities through ads or some other monetization. There is mixed length format videos now. So you need to cater to both long form video as well as short snackable videos for all users. Next is large inventory to rank. And this is mostly due to explosion of user generated content. User connections are more trusted than media organizations and brands generally. And there is appetite for quick casual video content. And that is mostly preferred over polished video production these days. So we need to serve these use cases very well. On the challenges, we need to optimize for multiple objectives and stakeholders. And here the trade-offs are often very difficult to reconcile. There is bias in training data for these models. For example, exposure bias, where you are only training the model based on whatever was already shown to users. There is position bias, where we know that something on top of users' feed is watched more than something at the bottom, even though they are both equally relevant. We also need to mitigate bias in prediction events design, because we want to rank both short and long form video together. There needs to be some creativity here. So if you rank only based optimizing for watch time, you will tend to favor longer videos. But if you kind of optimize for percentage of video watched, you will favor shorter videos. So we need to find an optimal ranking events to rank both type of videos together. Then better personalization. I think this has always been there. Nowadays, with bigger models, you need to capture higher order interactions to find the most relevant videos to the users. So these are the challenges currently in this area. We'll look specifically into challenges into multitask learning now, which is trying to solve the problem of, you have different types of events. How do you kind of predict all these well? So multitask learning is the paradigm where you're trying to combine knowledge from several tasks to help each other. So if you see on the left, it's a diagram of a YouTube video recommender system. There they're trying to predict user engagement and user satisfaction tasks together. So for example, if you really watch a video for long, it's indicative that you like the video. So predicting both of these together performs better than predicting each of them separately. On the right is a review platform. Again, they're predicting reviews and sentiment together is better than predicting each of them separately. So the first challenge in this domain is on information transfer. So how do you improve information transfer in multitask learning? There has been a lot of work on negative transfer recently, and this is the paradigm where training multiple tasks together is sometimes worse than training each of them separately. And this is because each of the tasks can have different gradient magnitudes as well as directions. So how do you combine them so that the model performs better on all of them is not trivial. So we will go a little bit deeper into negative transfer here. So negative transfer is prevalent when you train over heterogeneous tasks. It's been shown in the recent paper. I think this is pretty intuitive, but it's been shown theoretically in the recent paper. If you see at the bottom, there are two kinds of models, multitask models. The left one has smaller shared module, and the right one has a larger shared module. So the problem is in smaller shared module, you will have higher negative transfer because there is more interference between different tasks. On the right side, with larger shared modules, there is a problem that there may not be any transfer at all. Geometry between tasks learned in multitask learning also matters. And geometry here is measured by covariance matrices. So misaligned data leads often to negative or suboptimal transfer. So if you see in the diagram here, we have a target task and we have two tasks. The red one is having the same covariance as the target task, and the green one is having a different covariance as compared to target task. So here we see the task that has the same covariance, the red one, mostly tends to have a positive transfer very clearly. The green one, which has a different covariance, has negative to slightly positive transfer. To address this issue, this paper actually proposes covariance alignment modules that are placed between the shared module and the task inputs. And this module is learned jointly to improve transfer and the model performance across tasks. So next, the problem is on optimization imbalance. So on the right top, you see that's the general model architecture where you have a shared bottom layer and you have multiple task-specific layers. There is one target task and there are several auxiliary tasks to help learn the model. In this case, the shared parameters of the multitask model are updated based on the sum of the gradients of all the auxiliary tasks. So there are two things that can happen. One, which is the auxiliary tasks completely over-dominate the learning. So, the target tasks are completely overshadowed by the auxiliary task. And the second one is auxiliary tasks are sometimes the gradients are too small in magnitude so that they don't actually contribute to learning of the target task at all. So there's this paper, Meta Balance from 2022. This is actually work done internally at Facebook, which proposes balancing auxiliary losses by manipulating the gradients so that they are kind of match the magnitude of the target task. And this is like a adaptive gradient like framework. So it's a flexible adaptive gradient adaptation framework. It strengthens the dominance of the target task. It actually also enhances the knowledge transfer from weak auxiliary tasks. Next, we'll look into like challenges with biased training data, different types of bias, and how we overcome them. So first one is conformity bias. And an example of this is a user could watch a video just because it has like a lot of views, for example. Even though it may not match their interests, they will just curious. So how do you disentangle user interactions that were driven by conformity bias, leading to inconsistency with their true interests when you learn the model? So this paper from 2021 actually proposes learning interest embedding and conformity embedding separately within the model. And these embeddings are learned jointly with the click loss that it's trying to optimize for. There is also added supervision if you see the discrepancy loss, which is trying to disentangle the interest embedding and the conformity embedding more. So it's trying to maximize the distance between the conformity and the interest embedding, so that allows disentanglement better. So next is position bias. Again, the problem is videos on top of feed are watched more than those at bottom of the feed, even though both may be of same relevance to the user. In this case, it's more tricky because again, position is not available during inference time. So how do you kind of give that information to the model and help it predict better? So for this, the Google paper, recent Google paper actually proposes factorizing the prediction into two components. So one is the relevance component, which is coming from the big part of the model. And there is a bias component, which is coming from the shallow tower. And the shallow tower is trained only on features that are contributing to the bias. For example, position or interface and stuff like that. And here the features are used with dropout so that, for example, position doesn't over-dominate in the inference. So both these are combined to get a final prediction from the model. So next we'll look into prediction events themselves and the bias. Then how do you basically effectively rank long and short form videos together in the recommendation system? We discussed the basic way of ranking, either predicting watch time or predicting percentage leads to bias in different directions. So this paper, again, recent paper from 2022, is proposing an unbiased watch time gain metric. So what it's optimizing for is what is the user's watch time compared to what is the watch time of all users on similar videos. So if you see the formulation here, it's like watch time of the user minus average watch time of videos of similar length and divide by standard deviation of watch time of videos of similar length. The paper shows that optimizing for this instead of optimizing for raw watch time leads to increase in mean watch time across videos of all lengths. It also shows the bottom charts show that the distribution is now more even. So the blue one was the old distribution where they were optimizing only for watch time. In that case, you tend to over-distribute longer videos. But if you see the orange chart, now optimizing for watch time gain, you kind of have a more even distribution. Finally, we'll look into challenges with better feature interactions, like how do you learn feature interactions better. So here the problem is designing model architectures to effectively capture feature interactions of a higher degree. So we know that different different architectures that even capture the same degree of interaction can have very different performance. And they capture actually different strengths and they have like non-overlapping information. So again, this work from 2022, published by Facebook, was on deep and hierarchical ensemble network, DHEN in short. The way it works is basically they recursively stack interaction and ensemble layers together to learn like interactions of different orders. So example of interaction modules here can be self-attention, deep cross-net, convolution, etc. This model is shown to be of higher quality because each module in a layer here is implicitly connected to modules in other layers. Also, it's pretty generalizable in the sense that you can have very flexible module combinations, and it's also a very pluggable modular design where you can change interaction layers and ensemble layers as you wish. Finally, a very quick summary of all the work here. We looked into what are the broad trends on video recommendations across the industry. We've seen that optimizing the system for multiple stakeholders and often like conflicting objectives is a very active area of research. There is a lot of ongoing work here. A lot of emphasis is on debiasing training data and prediction events to train and serve these models effectively. Deep learning model architectures are also like still evolving to generate better personalized recommendations from very large video inventory, and a lot of insights and results in each of the cited papers from the talk. Yeah, thank you for your attention.